By the end of this module, you will have a basic understanding on secondary pump application, how it works traditionally, and the Danfoss solution. The key benefits of using a VLT HVAC drive in secondary pump systems. Let me start the module with a brief description of the secondary pumping application. Boilers and chillers are constant flow devices. That is, constant flow of water through the device is necessary for efficient or safe operation. In order to provide constant flow, HVAC systems are designed with two independent water loops. The two loops are primary loop, secondary loop. Primary loop provides constant flow through the boiler or chiller, and secondary loop provides variable water flow throughout the buildings to air handling buildings or other devices with heating or cooling coils. Primary pumps in primary, secondary systems have the task of supplying a constant flow of water through the boiler or chiller. These devices have an ideal flow rate. Flow rates that are too high or too low can reduce the system efficiency and possibly damage the equipment. The primary pumping loop provides a constant flow so that the secondary pump can tap off as required to provide the variable flow that is needed by the building's heating and cooling coils. A common pipe connects the primary loop with the secondary loop to decouple the loops because it hydraulically separates the primary from secondary loops. In general, the connection is kept as short as possible to minimize the pressure drop. In secondary pumping application, the secondary pump draws a variable flow from the primary loop. The flow through the secondary pump can be less than, equal, or greater than the flow in the primary loop. When the secondary flow is greater than the primary flow, some of the returned water in the secondary loop is pumped back through the decoupled pipe without going through the chiller. We shall now look at a traditional secondary pumping system. Primary pumps are sized to manage flow requirements and drop in pressure in the production loop only. The larger secondary pumps are sized to circulate the water throughout the system. Decoupled from the primary pumps, secondary pumps no longer have flow constraints, and this system can utilize two-way valves on the cooling or heating coils and other energy-saving methods without any problems for the boiler or chiller. In a traditional system with two-way valves, as the valves close, when the building loads are satisfied, the discharge pressure increases. As the pressure increases, the system resistance increases, and the system curve rides up the pump curve to a newer operating point at higher pressure and a lower flow. Riding the pump curve results in a slight reduction in pump energy, as it can be seen by comparing the two areas. As more two-way valves close, the discharge pressure continues to increase. At some point, the system pressure may be so great that it forces the two-way valves to remain open, even though flow may be further reduced. This results in a loss of temperature control in the building and wastes energy. Take a look at the graph. It shows the riding of the system curve with the pump curve when there is low flow and high pressure due to the closing of valves. You have seen that, in the traditional method, the use of two-way valves in secondary system increases the discharge pressure, which may lead to loss of temperature control in the building, but provides slight decrease in energy consumption. So there can be temperature control problems, and we save a little energy. How can we eliminate problems and become more efficient? That is where Danfoss solution comes into play. In Danfoss solution, the best energy savings and temperature control are achieved by adding a VLT HVAC drive to the system. A differential pressure sensor is placed across the furthest significant load in the system and used as a feedback to the VLT HVAC drive. The differential pressure sensor should be installed across the coil and control valve to measure the total pressure drop in the loop. When the valve closes, the pressure increases and the flow decreases. Conversely, when the valve opens, the pressure decreases and the flow increases. This increase or decrease in pressure is detected by the pressure sensor and given as feedback to the VLT HVAC drive. The VLT HVAC drive will vary the flow of secondary pump to maintain this pressure drop. This sensor location ensures full compensation for the lower system losses at lower water flows. The addition of VLT HVAC drive allows variation of pump motor speed, and the pump follows the system curve. This provides greater energy savings and prevents overpressurization of the system and loss of valve control of the flow through the coil. Take a look at the graph. It shows the difference in energy consumption after the addition of VLT HVAC drive. You can also notice from the graph that, in Danfoss solution, the pump curve follows the system curve, resulting in less energy consumption. Let's go in for a quick check of your understanding before we proceed. In order to achieve the best possible energy saving, it is of great significance that the sensor detecting the required pressure is of right type and located in the right spot. It is therefore important to place the sensor where the load is. This also helps us to take the system losses into account, and hence, optimizing the control system. Take a look at the illustration. It shows the incorrect and correct placement of pressure sensor and the corresponding energy savings obtained. Thus we can infer that savings of over 50% can be achieved with the sensor placed in the correct location and with the correct differential pressure sensor setting. One of the benefits of using VLT HVAC drive is better building temperature control. It has been stated that, as the two-way valves close, overpressurization of the system occurs, resulting in the loss of valve control and building temperature control problems. Take a look at the graph. It shows the effect on static pressure as a two-way valve closes. The system operating point is the intersection of pump curve and system curve. The system curve is made up of two components: flow pressure loss. The pressure loss absorbed by the control valve. The diagram shows that, when the valve is wide open, the valve pressure loss is small. When the valve begins to close, the pressure increases, moving the system curve from point A towards point B, and the flow is reduced. The flow pressure loss is reduced because of the lower system flow. At point B, the pressure drop across the valve is large, and as the valve attempts to move toward the closed position, the valve will have to close against the full pump pressure. The increase in pressure can modify the control valve characteristics, and can cause loss of control, because the valve may be forced opened at low flow, resulting in overheating or cooling of the building. Another benefit of VLT HVAC drive is constant pressure drop across the valve. Take a look at the graph. It shows the constant pressure drop across the valve. With VLT HVAC drive and variable flow secondary pumping, the differential pressure sensor that is placed across the most significant load maintains a constant differential pressure across the coil and the control valve. As the load is reduced, the room thermostat senses the lower temperature and closes the valve slightly. To reduce flow, the differential pressure increases, and the system curve moves up the pump curve to reduce flow. The increased differential pressure signal is transmitted to the VLT, HVAC drive, and the pump motor speed is reduced, generating a series of new pump curves as shown. The pump rides the control curve and maintains a constant pressure difference between the control curve and flow head loss curve. The control curve is the actual pump head that must be maintained by the pump as the system flow changes. The pressure difference is the pressure drop across the furthest coil and the control valve, and is the set point for the VLT, HVAC drive. Maintaining the constant pressure difference means that the control valve is always partially open, providing a minimum flow through the secondary system. Use of a small bypass line to ensure minimum flow is not needed because there will be flow through the furthest system load. An advanced feature of the VLT, HVAC drive is the two-input or two-zone PID controller. It is known that it is not always possible to determine exactly where the furthest or most significant load in a system is. The VLT, HVAC drive incorporates a two-zone PID controller so that sensors can be located at 2 points, and the VLT, HVAC drive will control the secondary pump to maintain the required differential pressure at either point. Before ending this module, let me give you a brief summary of what we learned. In traditional method, we have seen that the use of two-way valves in secondary system lowers the energy consumption. But we saw that in Danfoss solution, the addition of VLT, HVAC drive allows variation of pump motor speed, and the pump follows a system curve, which provides greater energy savings and prevents overpressurization of the system and loss of valve control of the flow through the coil. We also saw the key benefits of using VLT, HVAC drive like better temperature control, constant pressure drop across the valve, use of two-input PID controller. With this, we come to the end of this module, describing the secondary pumping system.